presentation, identification of differential equation system with various input effect. Tatiana, please share your screen.
Yes. Good evening. My name is Karaseva Tatiana. The topic of my report is identification of differential equation system with various input effects. Mathematical modeling of dynamic systems is, Mathematical modeling of dynamic systems is an interdisciplinary tool for studying various processes in nature, society, and industry. A lot of methods have been developed to simulate dynamic processes. These methods belong to the analytical and numerical, parametric and non-parametric classes. The study of various system behavior often leads to analysis and solution of equations that include characteristics such as a rate of change of system parameters. An analytical representation of such changes are derivatives, and they're the basis of differential equations. Differential equations and their systems are the basis for studying in the mathematical modeling field. They are functionally applied in manufacturing. It is important for the development of various branches of science and technology. The theory of differential equations is characterized by its direct application for practical problems. Differential equations and their systems can be applied as a tool for modeling various phenomena in mechanics, chemical reactions, electrical and magnetic phenomena. The study of a wide range of problems connected with the strength of materials, biology, economics, shows that their solution is reduced to mathematical modeling in the form of functional dependence described by differential equations and their systems. The representation in the form of differential equations makes it possible to obtain a model that is suitable for further study. In this aspect, it is necessary to take into account the interpretability of the obtained results provided by the symbolic representation of differential equations. It is worth noting that they often contain not one, but several output characteristics when studying, for example, manufacturing processes. Systems of differential equations are applied to represent such process. This work analyzes a method based on a self-configuring genetic programming algorithm for identification of dynamic systems with input effects changing according to predetermined laws. Let it need to be solved the inverse problem of mathematical modeling for a process characterized by an arbitrary number of input and output variables. That is, build a model in the form of a system of differential equations according to the measurements of inputs and outputs. It should be taken into account that input effects can be changed according to the certain laws. Let us present a description of the proposed approach for identifying a system of differential equations. This approach will be based on a self-configuring genetic programming algorithm for identifying a differential equation. The essence of this approach is in the formation of an individual, a tree, that encodes a differential equation. The tree is built with sample data describing the behavior of the object. Their functional and terminal sets are redefined using the genetic programming algorithm. The terminal set includes a set of four input and output variables, a set of constants and derivatives. The functional set consists of the functions used by the algorithm to form the solution. The root vertex of the tree contains not only an element of the functional set, but also the information about the maximum order of the derivative for the given individual. An example of a tree is shown in figure on slide. The evolutionary steps of the algorithm were also substantially modified for the genetic programming algorithm operating with the differential equations. A starting population is generated randomly from the given number of individuals set to the initialization step. An order of the differential equation is not higher than the given value of k in the root node. An individual in the form of a tree is converted into a formula. Then the fitness value is calculated for it. The calculating derivative must be performed at the points of the initial sample in calculating an error of correspondence of the found solution to the true one. In this work, the output estimation of the differential equation from the points of the initial sample was performed using the fourth-order Runge-Kutta method. The peculiarity of the mutation in the proposed approach is a possible change in the root node containing the maximum order of the differential equation. In case of a change, mutation of the maximum order of the differential equation, the order of the derivative must also be changed. So, in figure on slide, a mutation of the maximum order for the given individual will entail a change, randomly choosing the order of the derivative lower than a new maximum order and other selected vertices. The approach based on the genetic programming algorithm helps to obtain a model in the form on an arbitrary differential equation without a priori knowledge of the structure. Thus, the genetic programming algorithm for the identification of differential equations can be the basis for the concept of dynamic object identification development in the form of the differential equations system. An example of the differential equation system encoded in the form of a tree is presented in figure on the slide. Consider a scheme describing an approach for the identification of differential equations system. The proposed approach provides a combination of several genetic programming algorithms. K genetic programming algorithms are required for K equations in the system. Each algorithm searches for one of the equations of the system. Then a population of individuals is formed in each genetic programming algorithm. There are potential representations of each of K differential equations in the system. The suitability for all individuals of each population is calculated. One-time complete enumeration of all possible combinations of individuals. Their order is not taken into account. The best individual is determined on the basis of the obtained values in each population. Further, evolutionary steps are implemented. Selection, crossover, and mutation. After the implementation of the evolutionary steps, the fitness is recalculated. The calculation of the fitness for each individual of each population is carried out by substituting in each of the equations of the system. The best individuals are selected as the remaining equations in fitness calculating. Then the specified stop criterion is checked. If it is not met, a new cycle is implemented. When the second and third steps are implemented, the numerical coefficients of the equations of the system are optimized by the method of differential evolution. A vector to be optimized contains the numerical coefficients of all equations and the initial conditions containing in the system a current combination of individuals. The proposed approach applies a self-configuring type of evolutionary algorithm. The success history adaptation algorithm is applied for genetic programming and differential evolution parameters containing numerical values. The population level dynamic probabilities method is applied for parameters with the choice of type. The following is an efficiency study of the efficiency of the method based on evolutionary algorithms to identify objects in the form of a systems of differential equations with various input effects. This slide presents systems of differential equations that were applied to study the considered method. The dependencies presented in figure on slide were selected as input effects. Data with different levels of noise, 5 and 10%, were generated based on each system of differential equations and each input effect. The sample size for each set was 30 points. Thus, 9 data sets were given for each system. Also, 30 runs were carried out for each set. Figures on slides present the correspondence graphs on the obtained models to the original samples. Green and blue lines indicate outputs of the original objects. Red and yellow lines corresponds to the outputs of the obtained models. If there are more than 2 outputs, violet lines outputs of the original objects and light blue lines outputs of the obtained models. Complete line overlap with minimal model error is possible. So, in the course of the work, the study of the quality of identification in the form of differential equation system for different input effects was conducted. Objects are represented by differential equation system of various types and orders. The resulting models describe the data well, regardless of the type of input effects. It is confirmed by graphical interpretation of the obtained values. Thank you for your attention.
Thank you, Tatiana, very much. So we have enough time to ask questions, so you're welcome.
Okay, I have a little question.
Yes, please.
So do I understand correctly that you have several populations and the fitness of tree in population 1, for example, depends on the tree in population 2. So is it like cooperative coevolution approach?
You understand correctly. I don't speak about coevolutionary. I think this is a parallel genetic programming.
Yeah, but fitness in first population depends on other populations, right?
Yes, yes.
Mm-hmm. Okay, I had some experience of implementing several trees in genetic programming, but I thought of a different approach that had one population, but every individual consisted of several trees, like a forest, for example. So your approach is actually in every population you have one tree for
Yeah.
the individual.
Yes, yes.
So I wonder which of these approaches is better. How do you think?
The idea of methods that one genetic programming algorithm find one equations.
Yes, I understand.
But
okay, this is just maybe to think about. What if we make one
okay,
algorithm
okay,
with several trees in one individual? Okay, thank you.
Does anybody have another question? Okay, I would like to ask one question. If I correctly understood, you make a kind of simulation to get data and then you build a model, yes?
Yes.
Okay, so can we be sure that your solution will be correct for another time period if you continue your simulation? So this is if I would like to know if your solution interpolation or extrapolation.
I study my solution and they have a symbolic accuracy. Symbolic accuracy to initial equation systems.
Okay, it's very nice, but can we prove we will have the same solution for any other problem, or maybe we are lucky for these test problems? How do you think?
I investigate my approach of a lot of differential equation systems, and we have a lot of symbolic accuracy.
Okay, very impressive. Thank you very much. Well, more questions? Well,